wanting to live a life of quiet solitude, but then I got the astronomy bug. It was Halley's Comet that did it. So. All right, so we looked at the galaxy from the inside because that's where we're stuck. And as far as we've sent physical apparati that can take pictures, they're all still in the solar system. So we've never had an outside view of our galaxy. We like to pretend that we know what it looks like, but we are piecing it together indirectly. Looking at infrared frequencies, we can see through all that thick gas and dust in the way, and we can get a better view of the edge-on look. The stars above and below here, for the most part, are just in this wedge that we're close to the middle of. So we're out in the edge. We looked at Cepheid variables, our Lyra variables. Their periodicity is related to their brightness. And so when we aren't sure how far away a given star is in a given part of the galaxy, we can find these special types of stars that are oscillating in their brightness and get a distance from their actual or apparent brightness and start piecing things together. So the overall structure of the galaxy is a spiral. It's actually more of a barred spiral. There's a bulge in the center of the galaxy. I don't have a laser pointer, I should. Oh, thank you. And then you got a thin disk stretching out from there. You've got a halo of material, very thin. You've got globular clusters, which are very old stars that are in snowball arrangements of hundreds of thousands of stars. So there's an approximate cartoony view of how our galaxy, or at least galaxies like ours, look. Thank you, sir. Edge on, we're out here, as I said, in the suburbs, away from the central black hole in the nucleus, about 28,000 light years out. The whole thing is about 100 to 150,000 light years edge to edge. So when you read your science fiction stories that have galactic civilizations going around populating planets and manipulating star systems and stuff, just realize that to send a message from here just to the, say, the capital near the core, you're going to have, what, 52,000 years to get a reply. I mean, we don't have a way around that. So science fiction writers have to come up with some fast and light shortcut or convention that is the tool. And as we'll play with general relativity and things later, once you open up that rule, then you also start messing around with time. So it gets messier than you expect real fast. So most writers just ignore it. They just say, okay, we can talk to people far away. We can measure the plane of the galaxy by looking at, measure the mass of the galaxy by looking at the stuff in the plane of the galaxy and the stuff that goes around the galaxy. Very similar to how the solar system is set up, that we have a whole bunch of stuff in a stable, mainly flat orbits around the center, and then we have stuff that goes up and down through the galactic plane. Our sun actually goes...
John?
Yes?
So we do have our planets circle in a galactic, in a plane.
It's circle in a plane around the sun. There's very, very close to the same rotational equatorial plane of the sun. The sun and the planets, almost all of them revolve around the sun in the same direction. Some of the planets individually rotate opposite, but we think those are because of impacts that have tipped them or changed them. But if you look at our solar system compared to the galactic plane, it's almost edge on. We're almost tilted vertically, flying face on around. It's about tilt like this. So we go around the galaxy like that. Yeah. And we ride up and down, like these yellow lines showy, right up and down like horses in a merry-go-round. And there was just a speculative paper. I mean, I wouldn't even call it up to hypothesis yet, because there's so many leaps it takes. Looking at the periodicity here, I might make this a news update for August, so to go over it. That you get the mass extinctions in our geologic record just after we've passed through the galactic plane each time. And the geologic ages, the Jurassic and the Triassic and Cambrian, and all those are defined by these huge die-offs of most of life on Earth. That's the boundary of each of those. So it is a life-centric clock that we set up there. And there is a rough periodicity that is similar to our passages through. And their hypothesis is, or if I would even let it be that formal, is that when we go through, we're going through the thickest part of the galaxy at this point. So you have the additional gravitational tuggings of all the stars in the plane of the galaxy. But they add in their paper the presence of what we're going to cover in just a little bit, dark matter. The dark matter settles down into the plane of the galaxy as well. Dark matter is a particle that we haven't detected yet. It does not interact with the electromagnetic force. So light goes right through it. So you don't see it directly. You can see its effects on the path of light because it bends space-time just like anything with mass does. So it turns space into kind of a lens-like effect, warping stuff. But that additional tugging of the dark matter plane, both of those with that and the additional nearby stars, disturb comets in the Oort cloud, send them in more frequently into the inner solar system where they can impact. So like the Yucatan Peninsula is hit by the Chicxulub, what is now the Chicxulub crater, that we believe helped set the stage for the death of the dinosaurs. They didn't all die that day. It maybe took thousands or tens of thousands of years for the collapse of the ecosystem to occur, but that's what we think ultimately did the dinosaurs in and allowed mammals to rise. So it started a new age.
So the obvious question is where are we on the periodic curve?
Oh, I'll get to that in just a second. Yeah. Another part they add to it, and this is where the speculative part goes a little further, is that we haven't detected dark matter particles. We don't know what they are, but our best hypothesis for what they are is that they are self-annihilating particles. So when they interact with themselves, they are their own particle-antiparticle. They vanish, you get a flash of gamma ray radiation. So one of the hunts that we have to try to verify that there is dark matter and what it's made of is to look for a spike in galaxies around us and out there at the frequency that we expect in the gamma ray area. That you just get these dark matter particles interacting with themselves more where they're more concentrated, and you're going to get this little background glow in places in gamma ray frequencies. So they say, well, with the sun, yes, but the Earth going through this denser dark matter layer in the plane, you get more dark matter particles that fall down inside the Earth. They pass right through us all the time. If they exist the way we think they do, there's uncounted numbers passing through you right now. They don't interact with you. But as they concentrate down inside the center of the Earth, they interact with each other more because they're now concentrated. You get more energy released from this particle annihilation process. It actually would heat up the Earth's interior, leading to increased volcanism. So you get more volcanoes, more large-scale volcanic actions, like Siberia is largely covered in a lava field, and from one gigantic long eruptive period. We see evidence around the world that huge long-term eruptions have occurred with a large content of magma released, significant change of the atmospheric constituents because of that. So we get it from below with the dark matter, and we get it from above due to surrounding stars and dark matter. So we get more collisions hitting, and we get more heating of the interior of the Earth. All right, so going to your question, where are we? We have just passed through. And so it takes 10,000 years or so for the Oort cloud perturbed objects to start impacting, and it takes quite a while for the increased heat inside the Earth to start making it out to the surface, but they say the wave is coming. So in the next few thousand years, we should start being hit again and getting the volcanoes really cranking up. So I don't know. Yes?
John, if you say these are self-annihilating,
Mm-hmm.
where are they generated? Otherwise, wouldn't they eventually just all be gone if they're self-annihilating?
Yeah, well, we don't really know what they are, so we don't know what processes could create them, but they are believed to have all been created during the Big Bang. So.
Well, it's kind of like matter and antimatter when we come into contact.
Yes, they are. Yeah, they are their own antiparticle.
But there's enough of them so that they're still on.
Yeah. We'll see that in just a moment. So here it is. We expect the way the galaxies rotate to obey Kepler's laws, just like it does inside the solar system. But dark matter is what is hypothesized to exist that explains why they don't. So when you have got a galaxy and all its little visible matter components and gas, dust, stars, and like that, you have at least 10 times or more in the dark matter halo around that, and possibly, as they're using, more concentration even yet down in the plane of the galaxy itself. So if you could see it, we'd be in a bubble of opaque nothing. If it interacted with visible light, the electromagnetic force, then yeah, we'd all be in this deep dark cloud of this stuff, and we wouldn't even know that our galaxy's anywhere else. So where we expect stars in orbit around a galaxy's center to slow down, they don't. They continue to go as fast as they do closer in. So the galaxy starts to act more like a solid object, like a CD or a record, than a bunch of independently orbiting little particles. Stars being particles. So that's the mystery, and we have yet to solve that. So the dark matter moniker, is that the right use of the word moniker, applies to the fact that it doesn't interact with light. So there's nothing that reflects off of dark matter. Dark matter doesn't absorb light. It doesn't emit light unless it annihilates. But it's also dark in that we don't understand. So dark energy.
Wasn't that, I mean, that was more like a postulate because they considered there's so much missing mass in the universe. What is it? So
Well, we're going to get to that, yeah.
Using dark matter.
Well, at this stage, dark matter arises out of necessity for how galaxies rotate, and also we'll get to clusters of galaxies. Galaxies come in swarms or clusters, and they kind of wander around a center of gravity as well, but their individual galactic velocities are way too high to have remained close together as well. They also should have dispersed, but even though they have high individual velocities, something's still holding them together, and it's that 10 times more mass that you still need to get from dark matter. So it applies even on bigger and bigger scales. And there's other approaches, we'll talk about this later, but modified Newtonian dynamics called MOND, saying that, well, maybe just the laws of gravity as Newton saw them on the tiny scale of planets and solar systems just breaks down on the larger scale. That the gravity acts stronger. Of course, Einstein's formulation of gravity with general relativity would have to be modified as well to account for this. And there are physicists working hard to throw a paper out every now and then saying, okay, we don't have dark matter, quit looking for the particles. What we have is gravity acting differently than we expect. And so there's camps out there working on that. It's definitely not the favored camp. It's not what the bulk of the physics and astronomy community subscribes to. So we believe that galaxies form similar to solar systems with a big cloud of gas and dust. At this scale, we know that dark matter, or whatever the dark matter force is for the Mon people, that's weird, helps form the initial body that starts rotating. As it rotates, it collapses down, and you get a disk and everything that we see. So galaxies can either kind of be amorphous messes at first and settle into an elliptical galaxy format, or they can flatten down and form spiral arms with a central core. For a little while, there was some evidence that the quantity of dark matter was the difference between these two. So a spiral galaxy has a lot of dark matter with it, where an elliptical galaxy does not. And then quickly observations came out that proved that that rule doesn't hold. So that would have been very sweet. That would have been a very nice visual measure of dark matter, but no, that doesn't work either. We are in what is called the Orion Cygnus arm. So if you look on the wall over there where Orion is, I believe that is the arm behind us, and Cygnus is over here, and that's the arm ahead of us. So it goes through us on both sides of the sky like that. Here's the Orion Cygnus arm. So I think this is the Orion direction and the Cygnus direction over here. Out from here is the Perseus arm. In from us is the Sagittarius arm. And the center of the galaxy is down this direction. In the center of the galaxy on our wall is right here where Sagittarius is. There's the teapot spout. The central black hole is in the steam portion coming right out of the teapot. So right in there. So there's another galaxy that approximates what ours probably looks like from above, but again, we haven't had time in all of human civilization to get this picture. If the civilization that died out before the Egyptians, which we didn't have, had sent out spacecraft, they still wouldn't be in position yet to. The Atlanteans, right. Yeah, thank you. That's exactly what I was going for. We will get a mention of Stargate Atlantis in just a little bit. So. What are these spiral arms caused by? Well, these spiral arms are caused by new young stars. That these are, the overall density of material in the galaxy's disk is pretty uniform. It's pretty uniform. It isn't a big collection of material here and near vacuum here compared to that. These are shock waves traveling through, causing a lot of the gas clouds to begin collapsing and forming stars. And the stars that we see at great distance are the big bright stars, the O and the B type stars. But they only last a few 100,000 to a few million years. So as the shock wave travels through, creating all the stars from the smallest, dimmest, trillion-year-long living red M-type stars, what we see at a distance are the big bright stars that only last for a while. So the shock wave is traveling through, and then here, and then behind they trail off with the big bright stars dying off. So you're more likely to see your big supernova right on the back edge of a of a spiral arm.
Question?
Yes.
Shockwave created by what?
It seems, here's another picture of that. It's the same physics that you see when you see water going down the drain in a bathtub. You'll see little jets coming in at high ridges of water and little troughs in between. It's just how water piles up at different velocity as it's moving. We get the same phenomena in a tornado, that as a tornado vortex is going, you always have the story of how the wall was torn down and the car was flipped, but the china cabinet was sitting here with all the little china just sitting upright. And as the tornado is going along, you get these high speed jets that as the tornado turns and moves, you can get a little wedge of calm left right in there. And so it's just a natural way that things rotating will set up alternating ridges of
Created by the rotational speed.
right.
It's a gravitational phenomenon.
Yep. So same physics applies on the tiniest, works on the biggest. At least that's our assumption. So the nucleus of our galaxy has a massive black hole, 2.7 million solar masses down in there. Stars are only 860 Earth-Sun distances, AU, away from the core, zip around once every 16 years. Zooming in, here's I think a visual picture, the best we can get towards the black hole there. This is infrared, looking through the gas and dust. You can see a hot area there. Zooming from there further in, we can see gas and dust around this central hot area, going to, I believe, probably radio frequencies here. We can see some jets and spiral-like structure in here. Then zooming in, I believe this is back to infrared. We got the central black holes right in there. So the core of our galaxy, Sagittarius A, is the very dead center with the giant black hole. It is a very loud radio source that you guys have observed, right? You've picked up.
That's the subject of our STEM study this summer.
Yep. We do have a global network of radio telescopes that are working together, pulling in just untold terabytes of data, looking at Sagittarius A, the central black hole in our galaxy, and the next largest black hole visible from Earth is the black hole in the center of the galaxy M87, which is, I think, is up near Ursa Major, right? What's that? M87 should be on the wall, because you have two galaxies side by side right in there. Oh, I should have looked before. See, yeah, never just try to trust your brain in the middle of a talk. So it's out there somewhere.
Except the galaxy had the big supernova about 45 years ago.
I don't recall.
I can't remember, it was 87.
Yeah, I don't recall.
But it was up there by,
It was a supernova that was up near Ursa. It was a supernova up near Ursa. It was for a few days.
Yeah, I thought, are all the Messier objects over there? See, galaxies are the ovals, yeah. Oh, I'm looking in the blue instead of green. No, just not picking it out right now.
John, it's 86, is it 87 or 86? It's the cigar.
Oh, he's gonna look on the poster over there. Yeah, I'm not pulling up live. Can you look at the poster? See what 87, 87 is? I should have the constellation.
it says Virgo.
It's Virgo, okay. So A7 is in Virgo, which is right here. So it's in that, yeah, so it's in the cluster right in there. So it must be in the Virgo cluster. Yep, okay, good. We're leaving people with good information even if I started wrong. All right, so we got a grid here of radio telescopes spanning the face of the globe to create resolution. So you combine the data, and the technique is called interferometry, and you effectively get a radio dish this size of the entire Earth by taking all this data at the same time, combining it to using extremely precise time signature on the data. And what they're hoping to do is see the light, radio light, around the black hole in the center. This is a mathematical possibility. We might see nothing but noise. We might see a ring like that. We might see an off-center ring. We might see warped gooiness. We just don't know. So we are hoping to actually get a radio frequency image of the surrounding area of the event horizon of a black hole. So that's coming, I think, in the next year. So last night we had methane sources coming by the end of the year on Mars. So yeah, this is going to be an exciting couple of years with event horizons and life elsewhere. So we break galaxies into basically elliptical galaxy types, spiral galaxies. Some of them have a bar in the core rather than a round core, and then irregular galaxies. And so here's interesting hybrids, like looks like a giant core with a disk out here, an elliptical with a ring around it. There's a spiral. There's another spiral. Edge-on spiral. It's kind of our view inside of our own galaxy, but we're down in there. It's an interesting mixture of sort of a diffuse cloud of stars with a hint of a dusty spiral tilted in there.
M64.
Yeah. There's elliptical. Oh, nice L right there. You got some very diffuse ones. Irregular galaxies are largely probably because of collisions. Galaxies do collide. Big galaxies eat smaller galaxies, and galaxies collide a lot. And you get quite a period of chaos during that. I think it's not been updated, the new iOS, but there are galaxy simulator apps, so you can even crash galaxies together mathematically on your phone or pad and watch what comes out. You'll see, for brief instances, all the different shapes and interesting things you'll see out in the real galaxies out there. The Andromeda Galaxy, which is right up there, M31 right there on the wall, is headed this way. It'll be here in about 5 billion years to collide with the Milky Way. So yeah, if you buy property, just know it's going to be devalued when the galaxy collides. Our sun will be ending its life about that time too, so it's going to be a bad place. So it'll be beautiful skies at night, but the chance of any two stars directly impacting is nearly zero, even though you've got 100 billion stars each. Colliding is just that much space between them, and stars are very, very tiny. And astronomers have already named the resulting galaxy as the Milkomeda, I think. So, but I figure, in 4 billion years, 5 billion years, if there are still human descendants around, they can name it whatever they want. So. Another irregular galaxy, irregular galaxy. We had an old idea from Hubble that galaxies evolved. He's trying to apply biological evolution out into the stars, but we don't see that being causally correct. Pretty much you go from 0 to 12 billion years, and young galaxies will go through formation processes, settling down. You'll have ellipticals that age and spirals that will age. Eventually the gas and dust gets consumed and new star formation decreases. And so stars age and the galaxy becomes redder and things kind of wind down, just like us. So, and then you have irregular galaxies and collisions. So there's not such an evolutionary chain out there. I think this is where we stopped last time. So, well, no, I think when we come back to active galactic nuclei, we'll get to that. So we used astronomical units to map our way around inside the solar system because it's convenient. To get to nearby stars, we switched to light years and parsecs. Even inside of our galaxy, the number 100,000 light years or 150,000 light years is not a too cumbersome number to use. But when you get out between the galaxies, light years become pretty tiny. And so we switch now to million light year chunks. 3.26 million light years is a megaparsec. And so we start using megaparsecs as our easy units. So you're just not writing a bunch of zeros. CFID variables that I mentioned earlier, the variables that we can measure know their temperature and brightness by their period of bright and dim. And so we can see those out to 200 megaparsecs. So you're getting a good percentage of the universe out now and you can see an individual star in the outer edges of a galaxy. So that gives us a really nice yardstick to measure that far out. So here's the luminosity of the star, and they are thankfully very intrinsically bright stars, so you can see them that far. And their period in days, 3 to 100 days. So it's not hard to get observing runs that will let you observe multiple periods of the star and see its distance. So again, we're looking out, we're looking back in time. The moon is about 1 1/3 seconds back in time. The sun, like we saw last night, is about 8.5 minutes back in time. Nearest star that he put at Long's Peak is 4 1/4 light years away, so 4 1/4 years back in time. The Andromeda that's going to come hit us is about 2.5 million light years back in distance and 2.5 million years back in time as we see it tonight. And the edge of the universe is about 13.7 billion years back in time from us. So you are not seeing anything as it is. Even you folks are a millisecond or so back in time from me. So the only thought that I have that's actually in the present is what's in my head. Same with you guys, if you're real. Not simulations. So we talked about that. The most distant galaxy visible, we have clocked at about 3,000 megaparsecs, which is about 10 billion light years. The record distant star named Icarus, who we've seen because gravitational lensing, that the in between galaxies and dark matter, bent the light to act like a telescope for us, just coincidentally, is 9 billion light years away, an individual star. So that's pretty crazy. The record distant galaxy we've seen, 13.339 billion light years away. So from this, we can get the Hubble law, the expansion of the galaxy. Once you know well, we're going to get to that. You know the velocity that a galaxy is retreating from us appears to be. We can plop in the Hubble constant we have to figure out, and we can figure out its distance by solving for the distance. And the Hubble constant is its apparent velocity away from us in kilometers per second, and that increases for every megaparsec further out that you go. And our newest results are about 70 to 80 kilometers per second faster away from us every megaparsec you go out into the universe. And this is sort of a fit of some galaxies It's not perfect. There's other messy things that come in. So how we figure out the size and the distances of the universe come from this ladder of distances that from Earth into the solar system, we can actually bounce radar signals off of the other planets, and we can measure their position by getting the bounce back from that. We can, once we know the size of the solar system, and we know, say, how far Jupiter is, and we measure Jupiter's moons going around, then as Jupiter goes around to the far side of the solar system, we'll notice that the moons are not in the right place. They haven't quite gotten to where we predict them to be, because Jupiter is now further away than it was maybe directly out from us in the solar system. The light will not have reached us yet. So we can wait until the moons are where we expect them to be back in position, and we can get the speed of light figured out from that. And so we can get the speed of light and the size of the solar system figured out. We can also watch as the Earth goes across the solar system, the motion of distant planets against the more distant stars, and come up with a parallax way of measuring the scale of our solar system. Once we really have this anchored down, then we can use the orbit of the Earth and the parallax for nearby stars against more distant stars or way distant galaxies. And so we can directly measure through just trigonometry the distance to the nearby stars. Then we can start figuring out the nearby stars, how bright they are, what temperature and color and spectra they have. We can plot that, and we come up with really cool lines, main sequence lines for stars. And so when we see another star at a more distant location, we can figure out its temperature and color, fit it on there, figure out how bright it should be, how bright it looks, and figure out its distance. And now we can get stuff figured out all the way up to the size of the Milky Way galaxy. CFID variables and our Lyra variables are visible across the galaxy too, so that gives us an independent way to map the galaxy. But those CFID variables, once we have that really good, allows us to go further out into the nearby galaxies. We can look at nearby galaxies and their size, brightness, and morphology, how fast they seem to be retreating from us. Couple that with CFIDs, we have multiple independent ways to measure their distance. Then we can go further out into the universe and measure that. Sometimes we're lucky to get a supernova occur. Supernova have a certain brightness and decay of brightness based on their properties, and once we figure that out, we know how far away they are. So when we see the same thing happen all the way across the universe, where supernova can outshine, then we can measure all the way to the distant portions of the universe using an independent method there as well. You always want to get as many multiple independent ways to measure distances as you can, and then we can apply the Hubble law to go from the nearby galaxies to the more distant galaxies all the way out. So if you, as I said last time, if you came out and did a whole bunch of research and figured there was an error in how astronomy had figured out this chart, then, and everybody agreed that had been done wrong previously, then our calculated size of the rest of the universe would shift a little bit. Or if you came out and made a more precise measurement of the size of the solar system or something, or changed the speed of light, then everything else would be affected upward from that. So we probably have most of this down pretty well. It's pretty accurate. But we do our best to send out as many different methods to figure out the universe as we can. We do have colliding galaxies. We have all sorts of interesting shapes from galaxies that pass through each other. Here's two tidally interacting. You have swoops of stars thrown out from the collision. This is a close-up of the two galactic centers that are passing right in here. So this little box is this Hubble image right here. Things like a galactic collision can throw an awful lot of material down into the black hole in the center. disturbances to the galaxy seem to be what really cranks up the amount of material and collisions occurring around the central black hole. And when they go into their gobbling, eating fest down here, they will start to throw out gigantic jets of energy. So you'll have this traffic jam, basically, of material trying to fall into the black hole. It can't all get there at the same time. It heats up to tremendous temperatures. That gives you a pressure outward that inhibits some of the material from coming in. And the magnetic field of the black hole and the rotation of the black hole, the rotation of this material, creates these gigantic, near light speed jets of material that shoot out. And they can create lobes of radio emissions far out from the galaxy out here. So these are called active galactic nuclei. We had actually an educational product that we worked with that was a pop-up book for kids on active galactic nuclei, which seemed a little advanced for the delivery method, but it was an interesting, nicely made product. One of the items that outshine much of the universe made of the light, makes it from the very earliest ages of the universe, are quasars. Quasars were mysterious because they were tremendously redshifted due to the velocity away from us created by all the distance of the universe between us expanding. The quasars do change brightness pretty quickly. They can do it in hours or days. So astronomers knew that they were small because to have the entire thing change in some uniform way, even if it's a random way, it's all changing. The light source is changing in a small period of time. It's got to be a small object. But we couldn't imagine early on what would be that bright, but be able to change brightness on such a short time scale. And now we know that they are active galactic nuclei, that early galaxies had black holes eating a lot of stuff, and as they gobbled and burped a star, you'd have a brightness change, but these things are pumping out light that we could see today from out there. There's even a few quasars, I think, that large backyard telescopes can see. And you're seeing light from some of the farthest reaches in the universe. So here's the nucleus of a quasar and a jet coming out. Due to, in this particular case, due to a trick of its angle coming pretty close towards us, if you do a simple calculation of the velocity of the material here, it looks like it is going faster than the speed of light. Now, matter can't go faster than the speed of light. It's sort of an optical, mathematical, Einsteinian illusion, but it's pretty interesting. So when they were discovered at first, astronomers wondered if these were wholly new items. Maybe physics was totally different in these things because they were so bright, so small, that we just couldn't figure out what they were. And their spectra didn't match anything that we'd seen before. There just wasn't anything familiar in it. And then one enterprising astronomer said, wait a second, what if this is just this tremendously shifted over? And people said, well, they would have to be moving at unbelievable velocities and be unbelievably far. And that makes them unbelievably bright. So it was a hard pill to swallow. But once the idea that they could be tremendously shifted, so these lines up here, sorry, went the wrong direction. These lines are way over here. Then it all clicked into place, what we had. We had objects out at the edge of the universe far, far back in time that were putting out this amount of energy.
About the third of speed of light, right? These numbers are right.
Yeah, and this one? Yeah, this one probably is, yeah.
630 to 400.
Yep. The Z shift is what we look at for the sort of a, what is it, how to best say this? It's kind of like the previous slide there, that you get an apparent shift, an apparent velocity that exceeds the speed of light. So z of 1 is the speed of light, z of 2 is twice the speed of light. And so you can get shifts even greater than the speed of light as it looks, because it's not the object that's moving, it's the intervening space between. So, but, all right. The light's in transit on the way here, so it gets here, it's just stretched out. So there is a horizon, I don't remember what the z value is of the horizon, in which we would never even get the light.
It's not a Doppler shift, it's the fact that space is expanding too.
Yeah, but it is a shift. Yeah, it's the expansion shift of light. Yeah, and beyond a certain point, though, the light will never reach us. It's called the Hubble Bubble, which is a great name. But that's actually larger than the visible universe right now, back to the cosmic microwave background radiation, or we wouldn't see it. So the Hubble bubble is a mathematical bubble beyond that. So it looks like the universe has an edge, but it doesn't. It's probably very close to infinite. We'll talk about the large-scale structure of the universe as we, either next week or probably next month, August. So here's another image of the core of an active galactic galaxy, active galaxy with jets coming out, these huge lobes. There's a hot spot over here, another hot spot over there. Really fascinating. If your solar system in that galaxy were unfortunately there, you'd be just cooked right out of existence. So. There's another artist's conception of the crowding material heating up, trying to get into the black hole in the center, completely obscuring what's going on in here, and then the jets of material being punched out the north and south magnetic poles. That would be another artist's picture of the interior there. So you have the black hole with the accretion disk, unbelievably powerful magnetic field lines. I think there was a estimation that if you got within 10 light years of this, it would erase your floppy disks, back in the days that people had floppy disks. So 10 light years away or something, and your floppy disk is dead. So, and we find these massive galactic black holes by looking at the Doppler shift really close in. You'll have a high peak of velocity towards and away from you, rotation. All right, so we've gone to galaxies and galaxy cores. Now let's look at clusters of galaxies. But it is 11 o'clock, so let's take about a 5-8 minute break. Testing.
Yep.
Okay. So we figured out my brain miswire. So M87 is in the Virgo cluster. It's right over there behind Leo. And the double galaxy that I was thinking of is M81 and M82, and they are over here in the circumpolar box on the wall. So they are in Ursa Major. And that was my brain fart. So. All right, so going to the bigger stuff. So galaxies come in clusters, as I hinted at earlier. And within the closest 4 billion light years, there's about 2,700 clusters of galaxies that we know of, have identified. They are both rich and poor in density. Rich galaxy clusters are those classified as that when they have more than about 1,000 galaxies, a poor galaxies less. So this is a map of real data of galaxies, and you start to see something interesting with this filaments and nodules. This is missing data. There just isn't data there. So the famous Hubble deep sky image Took a look at the Big Dipper. Ursa Majors is coming up as a theme today because you are looking up out of the galactic plane. So let me go back to the wall again. So if you go looking through Cygnus and down past Ophiuchus, down to the core of the galaxy, down to the wall plug here around Crux, and then up to Perseus over here, that big U shape, can you see on the wall that there's a lot of additional stars in that U? Just more dots plotted than in here. So that's the plane of our galaxy. And so up here is pretty close to the galactic North Pole. So you're looking through the thinnest part of our galaxy out into intergalactic space. So if they took a picture here, was the thinking, they'd have the greatest chance of missing stars in our galaxy and just get a really good picture. And it barely, or almost didn't happen. I guess it was very controversial that they would take a whole bunch of Hubble Space Telescope time and focus on one really dim, dark area. So in that little teeny box there, we blow up and take a look at a picture of stars and galaxies in here. And they kind of found a little corner here that didn't have any bright stars or galaxies in it. So it's a really blank little area. So you're looking in a sort of happenstance blank area in the middle of a very otherwise blank part of the sky. And they just left the Hubble telescope there to stare. Took hours and hours of exposure, and they got the Hubble Deep Field. And they found thousands and thousands, I don't remember what the count in here, maybe it's like 10,000 galaxies or something like that in this image. There are just a few actual stars, so they have the little spikes coming off of it. So there's a star, I think that's a star. There's a star right there. There aren't many actual stars. Almost everything in here is a galaxy. Most of them with 10 to 100 million stars each.
The darkest part of the sky that they could find.
Darkest, emptiest part of the sky they could find. This is what they got. It gives me chills down my overly exercised legs. So just amazing. I mean, you can just gaze at that. So of course, once you do it once, you got to do it again. So the ultra deep field took another blank spot near Orion, about 1 degree square, and stared again. And yeah, you can go to another part of the sky and just find galaxies. There's a star down here, star right there, star up there, but just galaxies off in the distance. And it's probably a pretty good approximation. This is one of the tricks I tell people can do just out in the nighttime sky. It's not exactly true, so take it with a grain of salt, because stars are intrinsically brighter and dimmer than each other. But for just a gut feeling of the nighttime sky, you can go out and look up and imagine that the brighter stars are closer and the dimmer stars are further, and the dimmest stars are even further yet. And it's an okay approximation to give you a 3D depth to the nighttime sky. Here, galaxies come in different sizes, but smaller galaxies are probably more distant. But another indicator you have would be color. Now, older galaxies will be redder as they run out of the hot blue stars that make them up. But also stars or galaxies that are more distant will be redshifted more. And so, to an approximation, dimmer, smaller is going to be more distant, but redder will also be more distant. It's just something that's intrinsically larger and brighter. So you can kind of let your brain create a 3D image. Well, they're not perfect ways to measure, and so if you really want to do it, you got to go out and do it. But we actually have in the app, where is it? Sky Safari Pro. I think it's for $20 or $40, depending on whether you get it on special. It's a big honker. It takes a couple gigabytes of your phone storage. But for an additional purchase, you can get the latest galaxy survey on your phone. And you can actually see the three-dimensional structure of galaxies around us on your phone. Unbelievable. And you can do it really smoothly. You just kind of zip on through. So here's a zoom in to one area. Here's a star. So here's just a close-up. I don't know which. I think it's that one right there. Yeah. Got these two galaxies here. So you can see that there's galaxies all the way back in here. And just imagine, you got millions, tens, maybe 100 million stars in each of these dots. And each of those may be surrounded by up to 1 trillion planets. Tiny fraction of those could be in the habitable zone. I mean, that's an awful lot of territory out there. And they went to the southern sky and did the Hubble Extreme Deep Field, and it still holds true in the southern sky that if you pick a blank dark area and just let the space telescope add up hours of light, then you get just galaxies upon galaxies upon galaxies upon galaxies. So this is one of the earlier surveys of galaxy position. So here you are. They're looking out into the distance, a swath of sky across a plane. And what we start to see are interesting structures. And we believe that this large-scale structure of walls or filaments of galaxies and galaxy clusters are aided in their formation by dark matter. Dark matter clumped together is drawn to itself gravitationally, leaving behind relatively empty holes in space. There's still stuff in there. There's probably a few galaxies, there some gas and dust, but the vacuum of space is probably a little better here than it is along here. Hey! Looking up and down out of the plane of the galaxy again, our galaxy gets in the way of seeing off into the universe, so we have a lot more noise and obscuration. Yeah, that's not the right word. But you can see all this interesting structure of walls and voids. Going further out, the 2DF Galaxy Redshift Survey looked at 106,000 plus galaxies and plotted them. Again, our galaxy's plane is here. You're looking out about 0.3 billion light years. And it kind of looks like brain matter to me. It's like, I got, again, lots of voids. And it fades off out in the edges here just because it becomes, they're dimmer. And so you had the limitations of the telescope camera combination and the technique that they're using to figure out the galaxy distances. So here's an overlap of four surveys, sorry. So you have the SDSS survey, the Gamma survey, 3, and the European Space, the VVDS wide survey, looking out 9 billion light years. And you can see it in this little sample here, and these swaths here, that as you spend more time and get better with your technique, you see the same structure close in, you just push the data further out and find more galaxies and more filaments and more voids the further you go. And eventually we'll have the universe mapped. I mean, just give us time. The plane of the galaxy will be harder. Things like James Webb would help because it's in the infrared, but we need far infrared or even millimeter telescope observation techniques to get through the gas and dust of the universe and see the galaxies that are much further out.
Question on that.
Mm-hmm.
Looks like, particularly in that center wedge, that the level of structure, if anything, increases, or the scale size of the structure, if anything, increases as you go backwards in time or further away.
Yeah, that may just be because the early universe was a lot smaller. And so the structure itself is being expanded by the expansion of the universe. So, what we'll see with dark energy is that empty space becomes more empty space. That's just a fundamental rule of the universe. We call it dark energy. So the more emptiness you have, the more emptiness you get. Where you have galaxies and matter and gravity pulling stuff together, that counters dark energy, and stuff tends to stick together as long as it can.
But it started out structured as well.
Yeah, very early on. We'll see that as we get into the Big Bang Theory, that very likely this structure is just an expansion on quantum fluctuations in the Big Bang. So the random jittering and wiggling of the atomic-sized universe is now painted across the sky as galactic structures. So spoiler alert, I'm giving away some of the punchline. It twists the brain, it's just... So does this go on forever? Do we have galaxies going further? Einstein assumed the universe was infinite and unchanging. Of course, he was wrong. It is expanding. But what does that mean? The structure of the universe, one point was kind of tackled by what was called Olberg's paradox, saying that the universe isn't infinite because here you are in a dense forest, okay? And as I look out into the forest, except maybe up here I'll see a little bit of sky through the trees, and at sort of eye level, my gaze is eventually going to hit something that's tree, a leaf, a branch, or bark on a trunk. And so if this is an infinite forest, then there would never, ever, ever be anything from beyond that would hit me that isn't tree light or light bouncing off of a tree. So if the universe is infinite, Olberg said, then as I gaze out into the universe, my gaze would eventually hit the surface of a star. From our point of view, you'd have nothing but a solid surface of star to see. So the night would never be dark. You'd have a blazing average illumination of all the stars. Of course, didn't know that there was the expansion of the universe and redshifting involved. Also, look-back time in the beginning of the universe with the Big Bang puts not a boundary in space to the edge of the universe, but it creates a boundary in time to the universe. So we have an edge of the universe, but it's back at the Big Bang. It isn't out there at a certain distance. So when we say the edge of the universe is 13.7 billion light years away, we're being kind of fudgy about it. We're being sloppy. If you could magically go 13.7 billion light years out right now and look around, you'd see what you see here. Stars and galaxies are all around you about the same. Yes?
So, I mean, do we know where the center of the universe is to calculate what those boundaries go in either direction?
The center of the universe is everywhere. Since the expansion of the universe came from a point, we'll get into the...
That's my question, do we know where that point is?
The most, I just actually said it a minute ago on a different topic, the most forward point in the universe, the only center is actually the middle of your brain, your conscious perception at this instant. So we all are our own center of the universe. You guys can see a little bit further in the universe beyond the cosmic microwave background wall in that direction, and I can see a little bit further in the universe this way by 10 feet or so, because your position is actually the center. Yeah.
Yeah, but don't they, I mean, we know that the universe is expanding, and we know what velocity and what direction these are coming from, so we should be able to go backwards in time and see where everything is coalescing. And we're coalesced at that point, because if it is expanding,
Right.
and we're thinking it's going to contract,
Right. Yep.
but
If you had your Wayback Machine that turned the cosmic clock backwards at super high speed right now, and you turned it on, it would collapse on you. And if you're on Mars, it would collapse on you there. If you're in the Andromeda Galaxy, it would collapse on you in the Andromeda Galaxy. So the center point is everywhere.
that's a little hard.
There's the concept of gravity brain.
I know, it's crazy. But we'll get into it, we'll play it. And a lot of this comes from this slide right here. It does explain that. Yes, you are the center of the universe, yes.
That's pretty egotistical, isn't it?
Well, it's actually the reverse too, because the alien Bleep Gurp over in M87, he can say the same. So, I mean, we've never met Bleep Gurp, but I'm sure he's a nice guy.
With a name like that, I'm not sure I want to.
True. All right, so the assumptions we make, and the assumptions actually behind that claim, come from these 4 points. Homogeneity, that the universe sees matter and energy equally distributed everywhere. Isotropy is that everything looks the same. To Bleep Gurp, or to the Andromeda Galaxy, or to Mars, or you and I, the universe looks the same anytime we look out in any direction. If you looked back at the Hubble image and picked the most distant galaxy and looked around, you'd still have the universe 13.7 billion light year radius around you there, even though to us, they're near the edge and way back in time. And so to them, they would see walls of galaxies and voids, maybe a little different structure, but basically the large scale would look the same. We also assume universality, that the laws of physics are the same everywhere and have always been the same. There's some there's investigation seeing if something called the fine structure constant in the atom may have changed over time from the early universe to today. I don't think that's gone anywhere. I don't think there's strong evidence of it, but people saw enough little niggles at the edge of physics to investigate it for a while. So universality still seems to work. And the cosmological principle kind of puts these together, saying that other observers would see the same stuff as we do. There's no preferred observation point in the universe. There's no special center, like he was saying. There isn't anything like that. And we'll see what the model of the Big Bang is as we go today in August, to see whether this is justified or not. So Einstein and the geometry of space-time. So I covered in the very beginning of the course, about a year ago, we talked about the history of physics. We talked about Aristotle having sort of the universe's perfect picture, that there's a harmony out there. You've got crystalline spheres. Maybe Earth is a mess, but the planets and the motions in the universe are all going to be harmonious and perfect. And each time we make observations, and once Galileo started looking and seeing there's mountains on the moon and there's spots on the sun and things like that, we started seeing things weren't perfect. Eventually we gave up the idea of perfect circular orbits and adopted ellipses as being the accurate representation of how things orbit. And then Einstein had his perfect picture of the universe that didn't change, even though his equations said that things should either be collapsing or expanding. And so he put his fudge factor in, the cosmological constant that fixed the universe to make it match his concept of perfection. At the same time, Hubble was out there measuring the redshift of galaxies and saw that all the galaxies pretty much are racing away from us. And the smaller galaxies are racing away faster. So that goes back to Hubble's constant from before. And so Einstein called that his greatest blunder and took it out of the equations. And his equations were saying the universe should be expanding, and he didn't like the idea. But again, it's not expanding into anything. This is not a bubble. 13.7 billion, we just keep hitting this point. It's a really good point. I paid you to come in and say that, didn't you? It's perfect.
The engineer in me that was coming out.
All right, so
Do a geometry problem there.
this bubble that we see around us with the cosmic microwave background radiation being the most distant thing we can get light from, there isn't something beyond that it's expanding into. We're looking back in time at what was. There's just a universe out there with empty space becoming more empty space. And so the model that a lot of people like to say in classrooms is like raisins in bread. And you want the bread to rise because of all the yeast you put in there. So you plop your dough down, in a warm place, you leave for a while. And the little yeast doesn't care where it is. There's an equal amount of yeast everywhere. That's why we think dark energy, this expansion, is what's called a scalar field. It just expands. When there's empty space, every tick of the cosmic clock, one empty volume becomes two empty volumes, and two empty volumes become four empty volumes. It doesn't care what else is going on. If galaxies are trying to hold themselves together, they can win for a while. That's great. But empty space becomes more empty space. Yeast makes more bubbles. And so the raisins get further apart as the dough rises. Now, if there isn't a lot of dough between two raisins, at the end time, they're not going to be much further apart. So the velocity that they've been moving away from each other is slower than what were initially two raisins in the dough, which are now much further apart. So when you do the calculation, like how fast have they moved apart, it's a greater velocity. So that's Hubble's constant. So when we have light leaving a distant galaxy, say really purpley light here, and remember Doppler shift is just the change in frequency based on whatever's happening to the wavelength. If the wavelength gets longer, you've shifted towards the red. You hear it when a fire truck goes by or a train goes by, or every time a car drives by, you hear so you got as it moves along. That's red shifting. The frequency is going lower towards the red end of the spectrum. For our eyes, red is a long wavelength, blue is a short wavelength. So because we're all human-centric, we call it red shifting. If something's moving away from you, then the light getting to, speed of light's a constant. Speed of light never changes. So speed of light in a vacuum is constant. So the only thing that can give is the distance between the wavelengths. And so we see something moving away from you as red shifting. Well, in this case, empty space becomes more empty space. So as this short wavelength purpley light is leaving this galaxy, empty space is becoming more empty space in the light beam as time goes on. That's the same as making the crest and trough of each wave further apart, which when we gets to our galaxy is now a lower frequency. It's a red frequency. So the white hot Big Bang universe has now been redshifted all the way down to the microwave part of the electromagnetic spectrum, as we'll see. But early on, the question, once Einstein gave us space-time is now a fabric. You now have this four-dimensional construct of space and time, and anything that has geometry has some type of geometry. And there are three ways that you can curve something. You can have it flat. You can curve it in a positive way, and eventually it'll curve back on itself. We call that a sphere. Or you can curve it negatively. So negative to 0 to positive. That's the only curvature you can do to some type of fabric. This is sort of a saddle, is the term we use. And we can test the curvature of something by looking at, say, the area of a circle. So if you draw a circle, then you go in and you carefully figure out how much material is inside, and if it equals the area of a circle, is it pi r squared, right? Yeah, pi r squared. And that turns out to be what's actually in there, then you know you have a flat sheet. If you draw a circle on a sphere and then measure how much stuff is inside, there's going to be too much stuff inside. It's going to violate the simple pi r squared. If you look at a saddle and look at how many the area inside the circle, it'll be less than you would expect from a flat geometry equation. You can do it with triangles too. If you draw a triangle and measure the angles inside, they'll equal 180. Here, they will be greater than 180. Here, they'll add up to be less than 180. So the universe is going to have a curvature. And if it was like this, maybe it's going to collapse in on itself. If it's like this, maybe it's going to keep expanding. If it's like this, maybe it just stays the same. So with all that kind of background, let's now look at the Big Bang. We're doing fine on time. We get to get into this. So here's Arno Penzias and Robert Wilson. They worked for Bell Laboratories. Going back to the different parts of my slides on all the way back to the early part, Bell Laboratories was just unbelievable. I mean, the amount of scientific understanding of the world, I mean, plate tectonics. They helped figure out that the plates were sliding around on the Earth and explained everything from volcanoes to earthquakes to everything. It's just fantastic. Bell Laboratories in '65 knew that someday we were going to be using microwave radiation to transmit phone calls. It's expensive to run cables everywhere. If you can set up some towers and beam some of the calls and do leapfrogging across the landscape, that's definitely the way to go. But you need to understand the environment that you're in. You've got this big sky above. What if there is some microwave source up there that would be a problem? So you have a tower on the horizon, and you've got a whole bunch of important communication going, and then something bright rises in the microwave right behind it. Now your antenna in the foreground is only going to see this cosmic thing outshining your important telecommunication signal. So they were given the job to figure that out. What's going on? And they discovered the black hole in the center of the galaxy. They discovered a Cygnus X1 black hole. They didn't know what they were. They just knew that they were radio sources. But there was a background hiss everywhere. It's an annoying hiss. Now, Soviet physicist Alexander Friedman had predicted this mathematically, but they hadn't. They're not astronomers. They're technicians here working away. And so they were looking for sources of noise inside their antenna. You guys never worry about noise, right? You're finding sources of it. There were pigeons that were living in there and pooping. So they crawled around in there and cleaned the poop out, and the hiss remained. So as one article said, it's the only Nobel Prize given that involved the removal of pigeon poo. So. And what they were seeing is the highly redshifted last glow of the Big Bang. This is the primordial background radiation. It's in every direction around us. The universe in the Big Bang model was extremely hot and dense, and we're going to go crawling through the Big Bang second by second eventually here. But what we have now was something that was basically the temperature and appearance of the surface of a star throughout the entire universe. They finally cooled to the point where light could travel freely. That super hot surface is so distant and so much empty space has appeared between us and it in 13.7 billion years that it now looks like it's only about 2.7 degrees. So this is the temperature of the volume of the observable universe, 2.7 degrees above absolute zero. We see the same phenomena occurring on every star. The star seems to have a surface. We call it the photosphere. You look at the sun in the telescope that makes it safe to do it. Solar scope, thank you. What you're seeing is the point where the temperature and density is high enough that light is still bouncing around too much that you don't get light from any further depth. At the surface of the sun, now, even though the density has not changed really at all at that point, it is a thermodynamic and electromagnetic change where the light can now travel quickly, 8.5 minutes, 93 million miles to get to you. Yes?
About the 2.7 degree and calling that temperature, I understand temperature as a kinetic property of matter.
Mm-hmm.
Is that a kinetic property of matter that they're observing, or is that a
It
property
is the
of space?
black body radiation temperature.
Of what? Matter or space itself?
This would be the matter that was glowing throughout the universe
Matter that is visible.
at the point the universe became transparent. Mm-hmm. Yep. So it's largely hydrogen and helium, a little bit of lithium, and yeah, not much else. Yep, very good question. So we've talked about black holes before and Hawking radiation. The black holes have a temperature due to the particles that are created in empty space and normally re-annihilate each other faster than we can observe them. They're called virtual particles. But at the very edge of a black hole, the event horizon, one virtual particle will escape while the other one gets sucked in. That puts a negative energy into a black hole, causes them to eventually evaporate over unbelievable amounts of time. The temperature of black holes are a tiny fraction of a millionth of a degree Kelvin above absolute zero of big black holes. And so the entire universe is much hotter than all the black holes that we know of that are glowing and Hawking radiation. So all black holes are, even if nothing's falling into them, not even one hydrogen atom is finding the black hole, it's just out in the emptiest part of the universe, it's still growing as it absorbs the energy from the Big Bang. So all black holes are still growing. There's a little bit of loss from Hawking radiation, but it's swamped by the glowing universe itself. But eventually, as the expansion continues, this temperature will drop and black holes...
Also pulling in massive amounts of matter around them, right, and accelerating.
If they're in a crowded environment.
Very high temperatures.
Yeah, if they're in a crowded environment. But if they're way out in the middle of absolutely nowhere, no matter is nearby to fall in, then they're still growing just from absorbing the Big Bang energy. Yep. Just light energy. Because E equals mc squared says energy and matter are interchangeable. So.
Again, they're not absorbing the matter that's at that temperature, they're absorbing
Radiation. Mm-hmm.
thermal radiation.
Yep.
Matter.
You got it.
By radiation.
Yeah, because photons, even though they don't have a rest mass, they have momentum. And the E equals mc squared, you can go photon to mass equivalent of a photon. So, yeah. All right, so our first look at this was a mission called COBE. Then the Wilkinson map and isotropic, I don't remember. WMAP, thank you. Made a much better picture of the baby universe. So this is the entire sky around you in every direction. So that point corresponds with that point with this point down here. So this is the entire sky around you. And these are tiny changes in temperature in the last moment the universe was opaque. So the red is 0.0002 degrees warmer than the blue areas. So that's pretty isotropic. The universe is pretty darn uniform in density, but these are density differences in the early universe. Hotter, more dense, cooler, less dense, by a tiny amount, but yeah, so there's the COBE result and the WMAP result. We've now had the Planck mission go up and measure this to even more precision. But more, you can see the same, there's a big dark patch there, brighter patch there, dark patch there, brighter patch there. So the overall structure is exactly the same, you're just seeing more of the fine scale detail here. So this is how the universe was not perfectly, completely uniform in the beginning. You can see with your eyes the entire universe right there. That's pretty shocking. That's just amazing to me. I don't know, just you thought staring into one little dark part of the sky and seeing galaxies upon galaxies in the distance is cool. Now you're seeing it all. And these fluctuations, these tiny variations, are also related to tiny variations in the density of matter and energy and dark matter. So this then relates as the universe ages, expands, and cools to the filaments and the structure of galaxies, clusters of galaxies, and voids that we see around us today. It's the same thing. It's just a tiny version of the universe that expanded to what we see today. This is when the universe was about 380 to 400,000 light years in radius. 400,000 is a nice number to remember. So 400,000 light years in size. So you could fit, let's do that real quick, 8 of our Milky Way galaxies across the universe at the point that it cooled to this point. I've never thought that through. That's kind of fun.
And you know what frequency, radio frequency this was at? Is this infrared or is it radio?
It's microwave, yeah.
So some gigahertz. So that's the photons emitted by the particles at that 3 degree K at that frequency according to the Planck curve.
You got it. Yep, exactly.
How big did you say that was?
400,000 light years, right? And our galaxy is 1,000. I know, it's 100,000, yeah. Yeah, so 8, yeah. So this is 400,000, so 800,000 light years across.
After how many years?
Well, we'll get to that. Yeah, it is about that size. Yeah, let me think about that more, actually. Well, we're going to get into the second by second. We'll see if that quick little thought I had is true.
That's our galaxy.
No, it's the whole universe. Our galaxy, I was using our galaxy as scale.
How many seen in galaxies and stars? 2 billion light years away.
It had to cool and expand. Yeah, this is the look back surface all around us right now. So this encompasses the entire universe inside of it. Yeah.
That isn't now.
Oh, okay.
That's
Yeah.
then.
That's then, yeah. This is 13.7 billion years ago. Yeah, we're going, okay, yeah. Saying that you could stretch 8 galaxies across may not be the best way to say it because, well, let's see, I'll have to think about it because it's the visible bubble. The universe is that size, even though the universe itself is vastly larger than that at that time. Yeah, I'll have to play with that. But I'll say that that's probably right, but we'll get back to it. So there's COBE's best resolution, WMAP's, and Planck's resolution. And what we're now looking for is polarization. Just like you have polarized glasses, when light reflects off a surface, it gets a specific orientation to the waves. When you put on polarized glasses, they block the polarized light that comes off of most surfaces, because most surfaces around you, you have an up and a down, and you like looking this way, they're going to bounce off and come off. So a lot of the glare and brighter things that you see in the summer and the daytime get blocked by the polarized glasses. But there's expected to be a polarization to the light coming from this last opaque state of the universe that tells us more about how gravity waves and like that functioned in the Big Bang in the early universe. And one of the things we're looking for is what's called the B-mode pattern. And this is kind of what we expect with the highs and lows and then polarization around it. Primordial gravitational waves with the polarization were claimed by BICEP 2 in March 2014. Then by June, other astronomers said, no, we don't think you're right. And in September 2014, the Planck experiment showed that they had not taken into account the polarization of dust in our galaxy, cosmic dust. So that gas and dust we started today's lecture with fooled these astronomers into thinking they had seen the polarization of the early universe beyond. It's hard. I mean, the universe is pretty polluted with gas and dust and stars and galaxies. If you just get rid of all those things, we could figure out what's going on so much better. So you have to subtract it, and you have to subtract those effects correctly. Using gravitational lensing, in 2013, the South Pole discovered in the Herschel Space Observatory used that, and they're pretty happy that they see evidence of gravitational lensing in the early universe to a 97% confidence. So here's the history of the universe. And we're going to get into the details of this, but basically at point 0, you have some little disturbance in a timeless, spaceless field of some kind, which our little human brains really don't grasp well. And that disturbance started basically a gigantic bank loan. And we're going to get into what that means. But gravity is basically playing a lending game with energy in the universe. And we'll see what that means. But one is taking from the other, and we're basically living in a huge Ponzi scheme. So the universe will end because of that. When the universe was very, very tiny, below the size of an atom up to the size of a present-day molecule, quantum fluctuations, the weirdness that we talked about in section 3 with the light and how weird light and atoms are, and quantum jumps and waves and particles being interchangeable concepts, was what the entire universe ran on. Weird, boily, bubbly, seethy space-time mess. Then something fantastic happened called inflation. In a very short period of time, the universe increased in size many trillions of times. Then that slowed down, and we're now at 10 to the minus 32 seconds after the Big Bang. So we're talking a very small period of time here. 1 microsecond out, protons formed. The expansion after the inflation period slowed down tremendously. Up to at the 0.01, so 1/100th of a second, nuclear fusion was able to begin because you have protons, neutrons, and electrons. We had 3 minutes in which nuclear fusion occurred. So hydrogen, which is just a proton by itself, combined with hydrogen with neutrons helping to create helium. And then at 3 minutes, the universe was too diffuse for that to occur anymore. So at this point, you start getting electrons settling down into some of the atoms. We eventually get to the point where free electrons are scattering. Now light can travel freely between the electrons and the atomic nuclei, and this is where the universe becomes transparent. So the universe is neutrally filled with neutral hydrogen, helium at this point, no stars, so this is called the dark ages. This is at the 380,000 to 400,000 year point. So this is the cosmic microwave background radiation. This is the wall in time that we can't see before, because back here it was too hot and dense, just like we can't look into the sun with our best telescope, it's just brightness. Looking back in time further, you have nothing but brightness. You can't see, light doesn't travel any distance between atoms and electrons. It's also this point that we hope to see the polarization signals. So we have gravity waves. Basically, it's sound waves traveling through this dense universe. It's ringing like a bell. So if I knock this, the sound waves are traveling around inside the solid. Some of it comes out to your ear, but if you were inside this table, it would sound very differently because of the density of the table. It's just like if you click things together out next to the pool, you can hear that. If you go into the water and listen, it sounds very different. Higher frequencies, the sound travels faster. It's just a different experience inside the higher density material. So here, sound is echoing back and forth through the universe and creating these density waves that's started by these quantum fluctuations. And so at this point where the universe becomes transparent, whatever happened to be going on in the matter of the universe, in dense, less dense, warmer, cooler, or polarized this way or that way, from the sound waves and the gravitational waves going on, is going to be frozen in that picture. So this picture right here is just the snapshot of the state of the universe at that point, permanently visible now across the entire sky.
Question.
Yes?
When were electrons formed in this,
We're going to get into that. It's back in this.
before protons?
Yeah, right in that. We'll go tiny. Yeah, we're almost at noon, so we'll go tiny slice by tiny slice next in August. Do that. You got the dawn of time, tiny fraction of a section. You have subatomic particle soup. Then it superinflates, and then it finally cools to the point that it becomes transparent. We have our image of the early universe at about 400,000 years old, and then we have our present day looking out at galaxies spread across the sky. So let me end with the newest findings of the numbers, and we'll break it down into flat universe and the early universe in August. So what we see now from the Planck, WMAP gave us the purple values, Planck refined them in the yellow values. I leave them up because it's just interesting to see how things have been tweaked a little. But we see that the universe is nearly flat. So when we were concerned about how flat the universe was, it is so close to flat that we don't really see any curvature, positive or negative. So triangles in empty space made by lasers are going to have 180-degree angles in between them. And circles will have pi r squared area inside them. Parallel lines in a positively curved universe will eventually meet, just like lines of longitude meet at the North and South Pole. But in the saddle or negative shaped curvature universe, parallel lines always diverge infinitely and get further apart. But they never meet, they never get further apart in our universe. This baby picture is at 375,000 years. I need to put yellow in there, 400,000 years, because that's a little closer to the current number. The universe is a mixture of about 5% normal baryonic matter. So normal baryonic matter is what you're made of in the air and galaxies and stars and dust. It's the stuff that we think of in astronomy. It's the stuff we study as planetary or astrophysicists looking at galaxies and stuff like that. It is only 5% of the energy budget of the universe. dark matter makes up just under 27% of the universe. So this mysterious, possibly self-annihilating particle called dark matter is a lot more of the mass, so 5 times the mass on the universal scale than the stuff that we think of as stuff. We don't see it, we haven't measured it yet, we don't know what it's made of, we have theories, we have more and more increasingly complex and sensitive instruments and experiments trying to figure it out, but we just don't have it yet. The rest of the energy budget of the universe is what I haven't even really done much more than allude to, is 68% dark energy. This is that anti-gravity-like force of empty space becoming more empty space. You got every tick of time, this little spot becomes 2, 4, 8 empty volumes of space. Doesn't matter very much on the Earth, doesn't matter in our galaxy, doesn't matter in our galaxy cluster, but between the galaxy clusters, dark energy really starts to matter. So where space is increasing, dark energy is actually accelerating this rate of expansion. The universe is not just expanding, it's getting faster. Dark matter is not cold, hot, or warm. It sets a limit on neutrino mass. We're not going to get into that right now. Universe is 13.779 plus or minus 0.038 billion years old. The Hubble constant is now narrowed down to really close to 68 kilometers per second per megaparsec. And through astronomical history, from Hubble's age forward, people had estimates as high as 200 and as low as 20 or 30 for this, so they just didn't know. The maximum Z, or the maximum redshift that you can see, is just about 11. And the first stars turned on only about 400 million years, 300 to 400 million years after the Big Bang. So that's got to be closer to the 400 plus. So it's pretty soon after the universe became transparent, stars started forming. The large-scale filaments of galaxies are the frozen remains of the subatomic-sized universe, the quantum fluctuations frozen across the sky. So old numbers, newest pie chart, dark energy is this, dark matter is this, normal matter and energy is here. What we see is the old ratios. In the early universe, dark matter dominated. Neutrons, photons, and atoms were the other part of the pie, and dark energy was not on the chart yet. So at the point that the cosmic microwave background radiation picture was taken, dark energy didn't even matter. So it is accelerating the expansion of the universe, and this percentage will continue to increase, shoving these two wedges down smaller and smaller as the total energy of the universe. So we're going to get into the specifics of the accelerating nature of dark energy and what it might be, and the expansion of the universe, and dark matter and ordinary matter, and models of stuff like that in August and beyond. So any questions? I know it's crazy stuff, but...
Maybe you're going to get into this, but it seems like I read something recently that based on how flat the universe is, our perception of what would you say, 90 billion light year radius might only be like 1/2000th of what's actually out there.
Well, with the flatness of the universe is theoretically infinite. And we'll talk about the implications of an infinite universe in future times. I know. And there's other models. There's models of the Big Bang that act like this, but actually involve membranes, higher dimensional membranes, universes that touch. And so what happens in that model is that the universe is completely empty, and two universes in the higher dimensional space touch, releasing a colossal amount of energy, a bang. Particles are extremely dense, energy is very dense, and then it starts expanding very rapidly, inflates super fast, cools down, creates matter, becomes transparent, galaxies and stars form, they spread out, dark energy spreads them further out, they decay to nothing, and then when the planes are empty again, membranes are empty again, they can touch again and start it over again. So there's a model that does that. So instead of a big bang in the point source, we have an everywhere in the universe, everywhere in the infinite universe at the same time, touches another universe every place in the same time, and fills with energy to maximum density, and then it expands away from there. So it's a different model. It's consistent, except if we can get to the point where we can measure gravity waves, we'll see a different gravity wave signature with the membrane model versus the quantum fluctuation model. So someday we may actually be able to tell the difference. Yes?
Well, you know, there was, I saw a show, I don't know, it was 2 years ago or whatever, and it was, they were doing research at the CERN laboratory where there was, you know, the two diverse views about an expanding, contracting universe, and one that's just going to continue to expand until entropy takes over and it just dies.
Yeah, we'll talk about heat death in next month or two.
Talk about that in the next month? Okay, 'cause they,
Yep.
I mean,
We'll get
what
there.
kind of upset me.
Yeah. Yep. Now we'll definitely see,
Probably have plenty of time to get used to the idea.
see how far away that is. So they're black holes, quantum space-time. Okay, yeah, it's pretty far away. If you're going to talk about the birth of the universe, you got to talk about the death of the universe. So. All right, so go out there, feel significant, don't feel insignificant. You are the same. Yeah, that's the takeaway right there. Yeah. Thank you very much, everybody.